Okay, so far in this part, the second part, we covered two topics. One is the general equation of motion for any vehicles, the forward motion, the traction force, and the acceleration and the rolling resistance, air drag, and the on gradient, that kind of aspects of vehicle dynamics. The second part was look at the specific dynamic issues for serious hybrid electric vehicles, especially with gear arrangements, energy conversion between engine, generator, and motors. And these are all sort of assumed. We kind of assume that we know all the parameters. Now, in this third part, I'm going to go through the specific design issues and their consequences of gear train design in electrical drives. Okay, so rather than saying, right, we know everything, over here we're going to look at some of the characteristics and the typical configurations for electrical drives. Okay. Now, the part of the reason, or one of the big advantages of electrical motors replaces internal combustion engines is that electrical motors tend to give you a speed and torque characteristics. It produces the torque at the right speed that is very similar to the demand for driving a vehicle. Whereas the internal combustion engines tend to only work really the best, give you the best efficiency in a very small window of operational speed range. Whereas electrical vehicles actually matches the kind of torque and a speed required, a relationship required by the traction for electrical for vehicles really well. It matches very well. First of all, you'll be able to start from zero speed, give you fairly high, for example. At lower speed or zero speed, give you high torque or traction effort, because that's when people really accelerate their cars or their vehicles most often. Okay, and you need to get up to speed and running. And then once the speed is up, electrical motors will hit a limit of a power rating. And so that the traction force or traction torque will reduce inversely proportional to speed. But that's okay, because once you get up to speed, you don't need high torque demand anymore. The torque is mostly used to overcome the running resistances, the running resistance going up a hill or the air drag. Now, these are typically relatively small compared with the initial acceleration requirement, the torque required. So most cases, you probably just need a single gear ratio for electrical drives. In many cases, whereas for internal combustion engines, we know, if you guys drive, you will know, a typical modern car will have at least 5 gears. Okay, that means 5 different speed ratios. Some cars will have 4. In olden days, some old cars have 4, and some newer cars will have 6. It's all because they want to optimize operating conditions for engines to get the most effective use of the fuel. But for electrical drives, you would get away with just one single gear ratio, so you don't really need clutches. And of course, it's even possible to get rid of the gears altogether. So, so you would actually have a connection between the motor and the wheels directly. There's no gear ratio. But again, that sometimes can be difficult to achieve because motors tend to give you relatively lower torque at higher speed. So the speed is a lot faster than what you would need for electrical vehicles, whereas torque is lower. So you need something is best to actually have some kind of a gear ratio there, just to make sure that to make sure you don't over design the electrical motors. Therefore, you keep the size of motor small. Okay, so there are some general issues here, but if we look at the general evolution of the use of electrical motors in vehicles, in road vehicles, it actually went through several steps. Now, if you look at this diagram here, what I have here is I have two tires connected via what we call differential gearbox. That is connected to another gearbox there. This one there in the middle is a clutch. Okay, so clutch allows you to connect and disconnect between the motor and the gearbox. Okay, now traditionally, before the electrical motor was used, this block here would represent an engine. So engine drives the gearbox through the clutch. They can engage and disengage and change the gear ratio here. And then the gear out of the gearbox drives the differentials. Differential gearbox is there to distribute the force or the torque to the two wheels evenly. Okay, that's another mechanical device that does that. So you have so the earliest replacement application of electrical motors in cars or in vehicles is to replace the internal combustion engines with the electrical motor, but keep everything else in place. Okay, of course, it doesn't really take the full advantage of electrical drives. It keeps the mechanical complexity of a conventional vehicle, which is really not unnecessary. Okay, now because the motors can be controlled in a much more flexible way than engines. But nevertheless, that was just one step forward, saying, "I'll get rid of the internal combustion engines for the drive, and we use electrical motors." But in most cases, that's not really necessary. So the next step is to say, right, let's say we don't need a gearbox. Sorry, let's say we don't need a clutch because we don't really need to change the gear ratios. Say a single stage gearbox. So you get rid of the clutch there and rely on the control of the motor for difference to give you the best performance or speed. So you have motor connect to the gearbox and then connect to the differential gearbox. Okay, and of course that will help to reduce the mechanical complexity and with the size and the weight of the mechanical transmission as well, because you don't need a clutch anymore. Okay, or sometimes you can actually make the manufacturing process simpler by saying, right, I have a motor, I have the gearbox, I have the differentials, I can put everything in a single unit. Okay, in a single assembly, so you put everything together, that just sort of fits onto the car. And of course, that requires the design of the electrical motor together with the gear ratio and differentials, how you actually can put them into the place and how you connect them to the wheels. That kind of issues will evolve. But essentially, it's possible to make them into a single unit. And of course, the downside of that is if something goes wrong, you have to take this assembly apart and find out where the problem is. But that's also the case for many modern internal combustion engine based cars. In the olden days, people can fix their own cars because there's minimum amount of assembly. You can see everything there, and you can take them apart. But modern, latest vehicles will be a lot more complex, and I wouldn't really try to do anything to the car. If anything goes wrong with my car, I just take them straight to the garage because it gets too complicated. Not to mention all the electronics involved. So that's another configuration. And of course, now if you think about electrical motors, because we can actually design them into different sizes, and so we can actually use two motors instead of a single one. One motor for each side of the wheel. So in this case, if you look at the diagram here, I have one motor. Let me just find them out. One motor here through a gearbox connected to this left-hand side of the wheel. I have another motor that through another gearbox and that's connected to the right-hand side of the motor. So if I need to drive the car forward with no turning, okay, I could ask two motors give me the same force or same torque, so therefore they drive the vehicles forward. Now in this particular case, you don't need the differential gears to distribute the torque from a single motor to the two wheels, because now I'm driving two wheels together, but independently. Because if I'm able to control the two motors independently, then it's possible. When I need to go around a curve, a street corner, I don't necessarily have to rely only on steer the wheels pointing to the direction of your corner turning. I could potentially drive the out wheel. If you say, for example, I'm driving forward, I'm trying to turn left, okay, and I could drive this wheel, the right-hand side of the wheel, faster than the left-hand side. So this side goes forward faster than the other side, therefore it turns. So that would help with the turning of a vehicle. Okay, you can still use steering wheel to turn the wheel pointing to that direction, but that would help. It would help dynamically. It would help with the efficiency as well. Okay, so we have two motors connected to two wheels separately via the gearbox. And the modern designs of electrical machines, with the modern design, it is possible actually try to squeeze everything into the wheel, because there's a space, inside of the tires, in the inner part of the tires. You can actually either you put a gearbox into the wheel, okay, and or you can actually put gearbox and the motor, both these components, into the wheel as well. Okay, so there's not much space needed, except what's inside, depending on different diameters of the wheels. You would save a lot of space, and of course it's more challenge. It would be more challenge to design a motor like that, because the tires tend to have a worse operating condition than what you sit underneath when the things are installed underneath of a chassis. because there's no suspensions to isolate the vibrations. You have increased what we call unsprung mass. Okay, that's not very good for the dynamic behavior of a vehicle. Okay, and also you need some kind of special gear set as well. It's something, for example, something called a planetary gear set rather than just a very conventional gear set, because you would have to have a very sort of thin space, but a sort of diameter. In diameter that can go up a little bit, but the space limitation is different from what you would do with a more conventional configuration, like what we said before, this kind of arrangement. Okay. Or and also it's been sort of proposed, or it's been sort of demonstrated, that it's possible to get rid of the gears altogether. And you design a motor inside the wheel, so the wheel is also the motor. That would require a particular specific design that typically, something we will get to at later stage, a high number of poles for the electric motors. So it's like an electrical gearbox rather than mechanical gearbox. But you fit the motor inside the wheel, and the challenge is how to produce the torque, or high torque that's required. But in general, these are the different configurations, but I would think at a very minimum, you'll be looking at something like that. A motor driving each wheel, or one motor driving two wheels through some kind of gearbox. So you need some kind of gearbox because it would make life easier for the electrical motors design. Okay, motors have high speed but lower torque, but whereas drive, you have high speed, lower speed, relatively speaking, lower speed, high torque demand. That's the configurations. But in terms of the characteristics of electric motors, this is what people would normally see. This curve on this page is what people normally refer to, or really it's very representative of an electric motor. Now on the horizontal axis, this is the rotational speed of the motor. On the vertical axis is the motor output torque. Now, electric motors tend to have three different working regions, or three different sections, or three different modes. Okay, it changes with this increase of the vehicle's of the motor speed. So at lower speed, if we look at this in three regions, the region number one is called constant torque. Number two is called constant power, and number three is called natural characteristic region. Okay, so I'm going to go through each of the modes individually and explain in a little bit more details. The first region is called constant torque region. Now that region is limited by the maximum current that you can actually have in an electrical motor, because motor torque is proportional to the current. Because if the current is limited, then the maximum torque is limited. So at lower speed, all the other issues are not critical. It is the limit of the electrical current fed into the motor that limits the maximum torque available to an electrical motor. Too much torque or too much current, you are risking of copper loss, that's going to increase the heat because the current generates heat on resistances. So up to a certain speed, up to a certain speed, you have a constant torque. That is really the maximum torque available. Okay, that's what you see here. This TR on this diagram, and up to until you get to the speed of omega Rm. Okay, now by the time you get to that omega Rm, the torque needs to go down. Okay, so the motor will enter the second mode. But just leave that for time being. The speed here, where at the end of the constant torque region, this speed, or the rotational speed, or angular speed, is known as the rated speed of the motor, or the base speed, base, B-A-S-E, or base speed of the motor. Okay, so any electrical motor will have a base speed, or the rated speed. Below that speed, the motor will be able to output a constant torque. Okay, be able to produce that torque below that speed. That's the first region. So from 0 speed to the rated speed. Now the second region, once you get to that speed, the rated speed, there's limit on the voltage of the electrical motors. Okay, now remember the first region, we have a current limit. Second region is due to the limit of the voltage. Now electrical power equals to V times I. Now I is limited in the first region. It can't go beyond that current. Then in the second region, if V is also limited, then P equals to V times I. That means power is limited. Something has to go down. Okay? Now, the control of electrical motors tend to ask for, or always ask for, more voltage as the speed goes up, because the back EMF issues, something that we will talk about, or hopefully we'll have a chance to talk about at a later stage. Okay, so if the speed goes further up, the voltage goes up, and then the current has to go down because there's a constant power region. So in the second region, the current will go down, the voltage will go up, but the power will be the same. Therefore, because the current goes down, therefore the torque it produces will go down as well. This is why you see the torque reduces as the motor speed goes up. It gets to the point of omega pm. Now this omega pm is known as the maximum speed or maximum velocity of the motor. Okay, so the first one, this speed is known as the base speed or rated speed. The point where at the end of the constant power, the speed is known as the maximum speed, beyond which we get into a third region. But it's rarely used, really, because the motor wouldn't be working the most efficient way. Okay? And this constant power region, this value there, the power here is also known as the rated power. It can't go beyond that. Okay? So the motor cannot produce more power. The third region is called natural mode. It's, sometimes people do go beyond the maximum speed. But once the motor speed goes beyond that point, it's not really that efficient anymore. Okay, and also the torque is reduced at a faster pace than the constant region. So the more you push the speed up, the very little torque you will have. Okay, that's would be a limitation or constraint for driving vehicles, because at a high speed you will need to at least be able to produce enough traction force to overcome the rolling resistance, and in particular the air drag. So going down is not really a particularly good idea. So in general, when we talk about the electrical motors for vehicles, provide the traction force for vehicles, we are really looking at the first region and second region, the constant torque and the constant power region. And so you'll be looking at this shape. So okay, let's go back a little bit. We're looking at this shape. So it's this region plus that region. Okay, so you will have this funny shape there. That's what we normally refer to. Go down from there to there. That shape there is normally we use to discuss how the control and the design of an electrical drivetrain. Okay, and ignore all that because that's not going to produce enough torque, or unlikely to produce enough torque. Okay, so that's really sort of basic characteristics of electrical motors. And in the next lecture, I'm going to discuss how we actually use this, to determine whether we can need one single gear set or more than one gear ratio, or what is the gear ratio we need, and how to do all the calculations. Okay, thank you.